Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello and welcome everyone. It is my pleasure to introduce Saeed Ali from University of Maryland. Saeed has been here before as an intern, and 2009. In 2009, and he's going to tell us today about Bayesian mechanism design via multi to single agent reduction.
All right, so my talk is about Bayesian mechanism design via reduction from multi-agent to single-agent mechanism. So I will start with a quick introduction of what the problem is, and then I will explain two separate approaches for dealing with this problem. The first one is called decomposition via interim allocation rules. The other one is decomposition via ex-ante allocation rules. So here's a quick introduction. So in mechanism design, we face an optimization problem. However, the input to that optimization problem comes from selfish agents who may want to misreport the input in order to manipulate the outcome in their favor. So we assume that the private information of each agent is called the agent type. And for example, if you have an auction for selling 1 unit of an item, then the private type of each agent would be their value for the item. And the performance of a mechanism is, of course, measured with respect to the actual types and not with respect to the true types. Therefore, in the mechanism design, we have to take incentives of the agents into account. Roughly speaking, mechanisms can be categorized to mechanisms with money and mechanisms without money. In mechanisms with money, usually you either want to maximize welfare or some other objective, which is typically revenue, but it could be other objectives than revenue. For example, if you have a job scheduling, you may want to minimize make span. For the welfare maximization, for the case of quasi-linear utilities, which means your utility is your value for the outcome minus your payment, the game theoretic aspect of the problem has been solved. Like you can get an optimal solution by using VCG, but computationally it could be NP-hard, so there are approximations for this. Another way you can look at mechanism design is based on prior, whether it's prior-free or Bayesian. So in Bayesian mechanism design, we assume that we know the distributions from which the agents types are drawn, whereas in prior-free, we don't make such an assumption. So in this talk, I will focus on the Bayesian settings, and I assume that agents types are drawn from independent distributions. And this is crucial for the rest of my talk. And I assume that further that the objective is something which is linearly separable over the agents. It could be welfare or revenue or any other objective. By linearly separable, I mean that the objective is some of the objective values that you obtain from each single agent, which is obviously the case for both revenue and welfare. And assume that the coupling constraints for the agents are polymatroidal. I will explain this later. The main result is that in such environments, you can reduce the complexity of the problem exponentially by doing a multi-agent to single-agent reduction. And this is without no loss in the performance.
So by Bayesian setting, you assume that you know the distributions?
Yeah, I assume that I know the distributions, that there is some distribution and I know the distributions.
So just you know or everybody knows?
Everybody knows the distribution and everybody agrees on the distribution. So these are critical assumptions. And so what I'm going to explain is a general framework which can be applied to a variety of settings. For example, can be applied to non-quasi-linear utilities when you have budget or risk, or settings even in the settings where you don't have money, or any arbitrary objective as long as it is linearly separable. Okay. And in most of my talk, I will try to focus on the mathematical problems that arise in this context in the abstract form, and I will try not to focus on the game theory aspects that much. So here also are some related work for Bayesian mechanism design. So these are mostly economists' work on simple cases where there is, you have 1 unit of an item, and you have either risk aversion or budget constraints, and most of them assume that the agents types are distributed identically and independently. So these are mostly symmetric cases. And these problems are really hard. Like if you move from welfare maximization to something like revenue maximization, the problem suddenly becomes so hard. Like as opposed to the welfare maximization where VCG is optimal, in revenue maximization, there is no like global solution. And for multidimensional types, again, this first two lines are economists' work. These are only about very special cases where the valuations have very special structure and it can be reduced to single dimensional case. And then there are some computer scientists' work, very recent work, that deal with a specific variants of like the revenue maximization problem. For example, in some special settings, like you have budget and you have a limited number of items, you want to, like you assume independent distribution, you want to maximize revenue, something like that. And then there is this very recent work which actually uses techniques which are very similar to the techniques that I'm going to describe in this talk, but they don't present it as a reduction. They will use these techniques to solve a specific problem of revenue maximization where you have independent, when you have independent agents with additive valuations for in a multi-item auction. Okay, so I will start with decomposition via interim allocation rule. This is a joint work with Hufu, Nima Hakpana, Jason Hartline, and Azarach Melekian. So actually the first part of my talk is the recent one, and the second part is something which is just me, and it's from last year. So this is the first one is the more recent part. So I will start with a quick example which should give you an idea of what it means by reduction from multi-agent to single-agent reduction. Consider any auction for selling 1 unit of item and suppose pick any auction that sells to the highest bidder and consider a truthful auction. Now, suppose I have 3 agents here. So T sub I denotes the type space of agents I, and these are symmetric agents, and each agent has 2 types. The high type has $2, the low type has $1 valuation for the item, and they happen with equal probability. Now, if you look at any auction which allocates to the highest type, you can actually see that when the agent 1, for example, beats A, he wins with probability 7/12, and otherwise he wins with probability 1/12 in expectation over what the other agent submits. Now, consider a single agent mechanism which does the exact same thing. Like whenever the agent beats A, he wins with this probability, and when he beats B, he wins with this other probability. And it's well known that in any truthful mechanism, once you fix the allocation, you can actually compute the payments corresponding to that allocation, which leads to a truthful mechanism. So from the perspective of that agent, that multi-agent mechanism is equivalent to this single agent mechanism. Actually, this equivalence holds in general, and it doesn't need to make any assumption about quasi-linearity, risk neutrality, budget, or anything. If you give me a multi-agent mechanism, and if you assume that agent types are distributed independently, I can give you a single agent mechanism which is equivalent for each agent.
Go back to the multi-setting.
I assume that the ties are broken uniformly at random.
Okay. But the parameters are exactly the same here and after you did the reduction?
No, I'm saying that if this was a multi-agent mechanism, ignore this. Suppose you have an auction which allocates to the highest agent. Then this is the expected allocation that this agent observed. Now, suppose I give you a single agent mechanism which allocates with these exact probabilities. Suppose there is no other agent. I just give you a mechanism that if you beat A, it allocates the item to with this probability, otherwise with this other probability. And what I'm claiming is that from the perspective of this agent, there is nothing different between this and the multi-agent mechanism. In fact, more generally, if you have a multi-agent mechanism, if you have independent bidders, you can induce a single agent mechanism on each agent as follows. Fix some agent, and for all the other n-1 agent, create dummy agents which are drawn from the distributions of those corresponding agents. Yes, simulate the other agents. Run the multi-agent mechanism on those simulated agents and this actual agent. And this actual agent will not be able to tell the difference between the simulated mechanism and the actual mechanism. And here is the point where it is important that the agents types are distributed independently. Because if the agents types are correlated, then the simulated agents types will not be correlated with its actual agent. So it is crucial that the agents types are independent.
So also one more thing. So like when you do the simulation, right? What's the benefit you're getting? What's like so you?
No, I'm not doing anything. I'm just
easy reduction, right? You're taking a multi-agent mechanism. You're coming up with a single.
Yeah, what I want to do is to go in the other direction. I want to, instead of designing a optimal multi-agent mechanism, I want to somehow design optimal single-agent mechanisms, because single-agent mechanisms are easier to design, because instead of considering all possible combinations of agents types, I have to consider only the types of one agent. So the space of possibilities is exponentially smaller. So that is the idea that I want to get to. Yeah, this is the other direction. I want to say that anything can be decomposed in this way. In general, I claim that any multi-agent mechanism, regardless of the setting, can be decomposed as follows. You can decompose it to a central allocation mechanism and a bunch of single-agent mechanisms, where it works as follows. Each single-agent mechanism communicates with the corresponding agent, and then the single-agent mechanisms simultaneously submit some probabilistic demands to the central allocation mechanism. The central allocation mechanism then allocates resources to these single-agent mechanisms in such a way that in expectation would satisfy these probabilistic demands. And then finally, the single-agent mechanisms decide exactly the final outcome corresponding to this agent. So let me explain this to you by an example. Suppose you are in a setting where you want to sell one car you have three agents, you have one car for sale. And each agent has a multidimensional type because each car can be customized in different ways before sale. Like you can, for example, let's say you can change the color of the car, you can install like a sport package. So each agent will have different valuation for the car based on how you customize the car. Now, consider any optimal multi-agent mechanism in this case. And for each, so the only constraint is that you can allocate the car to one person. There is no constraint on how you can customize the car. So this is clearly multi-dimensional setting. And for each type of each agent, so this is the type, capital T denotes the type space, little f denotes the probability of each type, and x is the expected allocation for each type. Take any optimal mechanism and compute this expected probability of allocation for each type in that optimal mechanism. Now, I give you an equivalent decomposed mechanism that does the same thing. Suppose for each agent I do the following. I compute a single agent mechanism for this agent subject to these allocation probabilities. What I mean is the following. Suppose I have given you these probabilities like 0.45 and 0.1, and I ask you what is the optimal mechanism for selling to this agent subject to the probability of allocation not being more than these red numbers. And suppose we have only this single agent, there is no one else. And I claim that this optimal single agent mechanism subject to this is exactly the single agent mechanism which is induced on this agent by the optimal multi-agent mechanism. So basically, you can see it as the following. You have a bunch of optimal single agent mechanism. When the agents submit their type, these single agent mechanisms submit their probabilistic demand. Like this single agent mechanism submits a 0.45 to the central allocation mechanism, and then the central allocation mechanism ensures that each single agent mechanism receives the resource with this expected with probability in expectation this much. So to define this formally, so far I'm considering a single unit of resource that we want to allocate, but this can be generalized. But I will stick to this simple example. Define T sub n as the union of all of the type spaces. So this is the set of the types of all agents. And without loss of generality, I assume that the type spaces are disjoint. Now, I define this vector x, which is the expected allocation for each type of each agent, and I will call it the interim allocation. So in the decomposition that I'm claiming, the central allocation mechanism implements this interim allocation rule. In other words, if each agent submits, reports a type according with these probabilities, then they should receive the item, like the resource with those red expected probabilities. And then each single agent mechanism is optimal subject to the interim allocation rule. So here are then a number of questions that we need to answer in order to be able to use this technique to design optimal mechanisms. First of all, when is an interim allocation rule feasible? So for example, suppose here instead of 0.45, I had a 1. That would be clearly an infeasible case, because what if agent 1 submits A and agent 2 submits C, and if this is 1, then both of the agents have to get the good with probability of 1. So that is clearly not feasible. And so the first thing is we have to ensure the feasibility of interim allocation rule. And suppose I give you an interim allocation rule which is feasible. How can you actually implement this? Suppose I have given you these tables, and I'm asking you to give me an allocation policy that would implement in expectation, allocate to each type with these red probabilities. How would you do that? And the third question is how can I compute the optimal interim allocation rule? And finally, the last question is, suppose I give you the optimal interim allocation rule. How can you compute the optimal single agent mechanism subject to this interim allocation rule? So I will focus on the first three questions, and I will talk about the last question later. So
what do you assume? You assume that you can have an optimal single agent mechanism.
Yeah, I assume that I can compute the optimal single agent. If you give me these red probabilities, I can compute the optimal single agent mechanism subject to not allocating more than those probabilities.
So the fourth one.
Yeah, that is the first question.
So this you assume that you have a black box for this?
Yeah, I assume that I have a black box for that, and I want to answer the first three questions.
So suppose you actually, like, I'm just trying to understand, suppose you have a black box but just optimal single agent mechanism, right? Because X is something external, right? I'm telling you, you have to assign to this guy, like if it says this much, you assign it to no more than this probability and so on, right? So is it without loss of generality that you can actually implement for any X, or is it something that is...
it's something that I assume, but for most of the, for all of the problems that I know of, you can compute this. Like if you can compute a single agent mechanism for some X, you can compute it for any X. And it has some nice property, which as I will explain later. Like the expected objective is always concave in X. I will get to that later.
So this is optimal single agent mechanism is optimal for who? For the...
So the optimal single agent mechanism is the following. Suppose I have only this one agent, and there is no other agent in the picture. And I'm only asking you to construct a mechanism for me, let's say to maximize the revenue from this single agent. And I'm putting a constraint on you. The constraint is the following. If agent, take this agent. If agent beats C, agent 2, then you're allowed to allocate the item with probability at most 0.45. And if he beats D, you're allowed to allocate with probability at most 0.1. What is the maximum revenue you can get in expectation from this agent, if that is your constraint?
So yes, I guess that's what you asked question. What is the objective function?
Oh, the objective could be anything. I'm assuming that any objective you want to maximize, let's say revenue. Okay, so for the rest of the talk, let's say we want to maximize revenue. But it could be applied to welfare revenue or any objective which can be linearly separated over the agents.
But just to be complete, can you just illustrate an example of an optimal single agent mechanism in this setting? So I want to...
Okay, so let's say, I can't compute it off the top of my head, but let's say, it depends on exactly what you mean, but let's go back. So let's say, yes, let's say this is the, let's say this is the setting you have, and you are constrained with these probabilities. So I can imagine that the optimal single agent mechanism here would be something like you either don't sell to this guy and always sell to this guy at $2. Like you set a price of $2, and if the guy beats $2, it's not a price. If the guy beats $2, you will allocate it to the guy and with this probability. And if he beats $1, you allocate it with probability 0. if you want to maximize revenue. So the setting I explained here originally was for maximizing welfare. But let's say you want to maximize revenue, and these are your constraints. The optimal mechanism here would be to sell at $2 with this probability, which is the maximum you're allowed to. And if he bids $1, doesn't sell to him at all.
Why not sell with the one?
Because if you sell at $1, what is the maximum price you can charge? The maximum price you can charge is $1, which means that you also have to charge $1 for this higher type, because he would lie to you if you want to charge something higher.
All mechanisms here are true.
So this X is an upper bound constraint.
It's an upper bound constraint on what you can do.
What is the F's there? F1, F2?
F1, these are the distributions of these types. Like F1 of A is the probability 0.5, he has type A, with probability 0.5 he has type B. And that is the allocation, the expected allocation that it receives, but I treat the expected allocation as a constraint when I want to compute optimal single agent mechanism.
Yes, 50% of
So
time
that
values it
expectation
value 2.
Yeah.
is over for the single agent mechanism. That expectation is over just the
random
of the mechanism.
Yeah, the random coins of the mechanism. But when you have multi-agents, but when you have multi-agents, this randomization could come from other agents. Okay, so here is formally the problem that we have. So from now on, I will just ignore all the mechanism design aspects, and I will just look at the following problem. Suppose I have given these tables, and I know, for example, that agent 1 has type A with this probability, and it has to be allocated with, it has to get the item with this probability. And I want to come up with some allocation policy which in expectation satisfies these red probabilities. Like whenever agent 2 bids C, he has to receive the item with probability 0.45. And the questions that I wanted to answer was whether these expectation probabilities, which I call the interim allocation rule, whether they are feasible and how I can actually come up with some allocation that implements them, and how we can optimize over X, and how we can compute the optimal single agent mechanism. So to give you an idea of how we can solve this, I will demonstrate a computationally inefficient solution for answering this question. So it's based on a network flow argument. So for every possible scenario of the agents, I will put one vertex. So each one is one possible profile of types for the agent. And for each type of each agent, I will also put one vertex on the right-hand side. And I will add a source node and a sink node. Now, I will add directed edges from the source node to each scenario, and the capacity of each edge is the probability of that scenario happening. And on the other side, I will basically set directed edges from each type node to the sink node, and the capacity of each such edge is the probability of that node happening multiplied by expected allocation that that type needs. So this is like a demand, and this is like a supply that you have. And you set the middle edges as follows. For each scenario, you add directed edges to the types that appear in that scenario. Like for AC, you add directed edges to A, C, and E. Now, if you have a feasible flow, if the maximum flow from source to sink saturates all these edges, then that means your interim allocation rule is feasible, right? And if you actually compute a maximum flow, the amount of flow in the middle edges exactly tell you how to allocate the item. Like, for example, if you're at this scenario, ACE, look at the flow that goes to A and flow that goes to E and flow that goes to, C and that E. And what it means is that if this scenario happens, you just allocate the item to one of A, C, or E proportional to that, proportional to the flow of those edges.
Are you assuming TIs are disjoint?
Yes.
Yeah, I assume that TIs are disjoint. If they're, it doesn't really, that is without loss of generality, because if they are equal, the same, I can relabel them differently.
Right, but it makes a difference to your probabilities, so that's why I'm asking.
Yeah, I assume that the type space of each agent are labeled in different ways. So even if they're exactly, they mean the same thing, I will just name them differently. Okay, but
here you're saying X is feasible. Actually, if you can give to everybody equal to X, right?
Yeah, exactly. If these edges are all saturated, that would be condition of feasibility. So as you can see, this network flow construction is exponential. So because you have a node for every possible scenario. So it's not efficient, but I will get back to this. I just wanted to give you an idea of how we can handle this. Okay, so let's capital X denote the set of all possible feasible interim allocation rules. And now, suppose for each agent, the R sub I of xi is the, like X sub I is the part of the interim allocation rule that is restricted to the types of that agent. So suppose this denotes the expected objective of the optimal single agent mechanism subject to this interim allocation rule. So first of all, we show that for any single agent problem with a maximization objective, this R is convex, is concave. And this is regardless of whatever objective you have or whatever the constraint on the single agent mechanism is. It's always concave. And therefore, you can compute the optimal interim allocation rules by just solving this convex program, which maximizes the sum of the single agent objectives subject to feasibility of interim allocation rule. However, this convex program is, of course, exponential size because we have the network flow construction is exponential. So we want to address this problem. So we want to check the feasibility of interim allocation rule and be able to optimize over them in polynomial time. So let's go back to this network flow case. The condition for, so if you can imagine these nodes as demand nodes and these other nodes on the left as supply nodes. In order for this network to have a feasible assignment that satisfies all the demands, the condition that you need to satisfy is that for any subset of vertices on the right, the total demand should be less than or equal to the total supply of their neighbors on the left-hand side. That is the necessary and sufficient condition. That condition actually was discovered by, it was not discovered, but it was proved to be sufficient by Border, although Border didn't use this network flow argument. He had a very complicated argument for proving this. And it can be interpreted as the following. For any subset of types, the total supply of their neighbors is exactly, so what are the neighbors of these types? The neighbors of those subsets are exactly the scenarios in which at least one of those types appear. And this is the total demand. So basically, it says that the total demand of that set should be less than or equal to the probability that there is at least one agent who's type in that subset. And again, you can see there are exponentially many inequalities, but this is now easier to handle. So now I want to give you a polymatroidal characterization of this space of interim allocation rules. So define a normalized interim allocation rule as follows. Just multiply the expected allocation of each type by the probability of that type appearing. And define this function g of s, where s is a subset of types, as to be equal to the probability that there is at least one agent whose type is in set s. Now, the set of all normalized interim allocation rules is a polymatroid defined by these inequalities. So because it's a polymatroid, you can optimize over it in polynomial time, because you can construct a separation oracle and to find a violated inequality by minimizing the g of s minus x bar of s for any given x bar. This is a submodular minimization. We actually show that you can do it very efficiently in time which is almost linear. Remember that T sub n is the set of all types, which is actually the size of the vector x bar. So this is pretty efficient. So you can.
So this is to check whether x is feasible or not, right? So
yeah, this is for checking. You get a separation oracle, and because you have a separation oracle, this is a convex space. You can optimize over this space using ellipsoid method in polynomial time. So you can compute the interim allocation rules in polynomial time. Now the question is, how can we implement the interim allocation rules? So if I give you an interim allocation rule which is feasible, how do you allocate the resources to satisfy these expected probabilities? So I will start by defining tight sets which turn out to be very important in our implementation. So let us look at the interpretation of this x bar of s. So x bar of s, when you have one item, simply has the following interpretation. It means the expected probability that there is a type from set S shows up and also gets allocated to. That is the meaning of x bar of s. It's basically the sum over. Okay, this notation means take the sum over all elements of. Like look at the vector x and sum over all elements of x entries of x that appear in S. And what is g of s? G of s is the probability that there is at least some type in set S. And obviously, this first one has to be less than or equal to the second one, because if there is an agent from set S who has appeared and has got allocated to, there must be some agent from set S that has appeared. But the important thing is that when the two are equal, that means whenever there is at least one agent from set S, then at least one agent from set S should get allocated to. Like if there are more than one agent in set S, it doesn't say whom to allocate to. But if there is at least one, you should allocate to that. So it somehow determines what should be your allocation in the case where you have a tight subset. And it's easy to show that tight subsets are closed under union and intersection because the tight subsets are minimizers of a submodular function, so they are closed. And therefore, tight subsets form a hierarchy.
What do you mean by hierarchy?
It means they are either contained in each other or they don't intersect. Like, I will show you in a second. Actually, you can show that when agents are independent, they form a full hierarchy, which means that there is some ordering in which every tight subset is contained in another tight subset. They are not. You can't have tight subsets that are disjoint. So here is an example. Suppose x bar is your normalized interim allocation vector, and in this example, these are the tight subsets. A by itself is a tight subset, and A, C, and E is also a tight subset. So because of that proposition regarding the tight subsets, what I know is the following. Like if I am at this scenario, for example, A, C, and E, because A by itself is a tight subset, it has to always be allocated. So in this case, there is only one choice. I have to allocate to A. And let's say, look at another scenario. Let's say the scenario is B, D, and E. Now, E is the only one in this type subset that has appeared, so I have to allocate to E, and there is no other choice. But now let's say if you have a scenario like B, C, E. In this case, you have two guys from one tight subset, and B is not in a tight subset. So definitely, by that proposition, I know that I cannot allocate to B, but it doesn't tell you between C and E which one I should allocate to. But now observe that if we had a scenario like this, where we have a full hierarchy of tight subsets, this would completely pin down the allocation. Because if you have something like a full hierarchy of this type, then basically when the agents come in, they report their type, you just sort them in the order defined by these hierarchies, and you allocate to the first agent based on this ordering. Right? So it would be nice if our interim allocation rule, normalized interim allocation rule, corresponded to some hierarchy, like some full hierarchy like this. And it turns out that the vertices of that polymatroid, the polymatroid of all interim allocation, feasible interim allocation rules, have that property. So let me define this formally. A partial ranking is a ranking of a subset of the type space. So basically, suppose S is a subset of types. Partial ranking assigns numbers between 1 and the size of S to these numbers. So it ranks them in some order. Every partial ranking corresponds to a vertex of the polymatroid and vice versa. Every vertex of a polymatroid corresponds to a partial ranking. And here is how you get from a partial ranking to a vertex of the polymatroid. You basically look at, let's say this is our partial ranking. What I will do is the following. I will start with a vector which is all zeros, and then I will start increasing the first element in the ranking, which is A. I increase A until set A by itself becomes tight. And then the next one is C. Then I will start increasing C until A, C becomes tight. And then I start increasing D until A, C, and E becomes tight. And at that point, I will stop because B, D, and G are not in the rank in the partial ranking, so their corresponding values will be 0. And this gives me a vertex of that polymatroid. And this, you can go also in the opposite direction. If I give you a vertex of the polymatroid, you can actually use a greedy algorithm to find a corresponding ranking. And the nice thing about these rankings is that you can actually deterministically implement the allocation rule corresponding to a ranking. Because if you have a ranking like this, then it means that whenever the agents arrive, they submit their type, you just sort them based on their type according to this hierarchy, and you allocate to the agent whose type comes first. And if for these other types, like B, D, and G, the corresponding interim allocation rule is 0, so you just ignore them, even if there is no type who comes before them in the ranking.
Have the same problem, right? You would not have total hierarchy because if two of them have the same x value, for example, right? They will go tight at the same time.
No. If you have a partial ranking, the hierarchies will be always strict. Yeah, I'm saying that if you have a vertex, a vertex always defines a strict ordering on some subset of the elements, and it gives you a deterministic implementation for that vertex. And now the nice thing is that if your normalized interim allocation rule happen to be a vertex of that polymatroid, there is a deterministic implementation for that. And if it is not a vertex, what you can do is that you can write it as a convex combination of the vertices of the polymatroid, and you can sample a vertex from that convex combination and then implement use the deterministic allocation rule corresponding to that vertex. And it turns out that you don't even need to write it as a convex combination. What you can do is that you can round this x to a vertex in such a way that every coordinate in expectation remains the same. So I will give a quick, this is pretty standard. I will give a quick sketch of how you can do this. So let's say this is your normalized interim allocation rule, and these are the tight sets that you have so far. Let's say C and E are both in the same tight subset. What you do is that you start increasing C and at the same time decrease E by the same value until for some delta this set A and C becomes tight. And you can also do the opposite thing, like increase E and decrease C until E becomes tight. And you can always show that at least one of those sets become tight before the other entry reaches 0. And this is always the case. And then you will randomize between one of these two updates with probabilities proportional to delta and delta prime. And if you do this at random, do the left thing with probability delta prime over the sum of delta and delta prime, and do the right thing otherwise. In expectation, the value of every coordinate remains the same, but you have increased the number of tight sets by 1. So if you keep repeating this thing, after a number of iterations, you will get to a vertex in which every coordinate in expectation is the same as your original point. And you can actually show that the number of iterations that you need is at most the length of this vector.
Well, but it's the same thing, right? You're writing your fraction solution
as it's exactly the same thing.
Just extreme points. Except in this case, you might even not have a small support, right?
But the thing is that if you want to write it as a convex combination of the vertices, it could be you don't want to write it as a convex combination of exponentially many vertices, right?
This would do that, right?
Yeah, this would do that, but the thing is, it's fine because we just want to sample from that convex combination, so we don't have to go through the trouble of writing it as a convex combination of a small number of vertices. We can just use this randomized rounding approach, which just gives me one vertex. It could be, you're right. The support of this randomized rounding is exponential, but we don't care about it. We just want to sample from this in polynomial time. So this basically gives me an implementation for any normalized interim allocation rule. So let's look at some generalization of this. So now instead of having a single unit of an item, suppose you have a matroid which specifies your allocation constraint, which means for any subset of agents, they can be simultaneously allocated to if their types form an independent set of the matroid. It turns out that the condition for feasibility and this necessary and sufficient for feasibility is the following, where the Rm is the rank function of the matroid. You basically replace whatever you had on the right-hand side of your polymatroid constraint with the following. This is the expected rank of the subset of types that have appeared intersection some set S that comes from your polymatroid constraint. And consider the case where you had one unit of item. In that case, the rank function is just the minimum of 0 and 1. The minimum of 1 and the size of the intersection of T and S. Which means if there is at least one agent whose type is in set S, this whole thing would be 1 if you have a rank 1 uniform matroid, and otherwise this would be 0. So this is exactly what we had before. But this is more general. This works for any matroid environment. And all the other things that I explained actually works for these environments. If you have a vertex again corresponds to a partial ranking, and what you would do to compute the allocation for a vertex, you would just go through that ranking specified for the vertex, and you look at the agents types, you try to allocate to them one by one if the current set of allocation remains an independent set. You basically pick a maximal independent set from every prefix of that ordering. And this can be actually generalized even more. Actually, the matroid itself could be randomized. So this is the same condition still decompose. And this is useful, for example, in environments where you have a stochastic supply. I will give an example of this. And this can be extended even to environments with polymatroidal constraints.
Yeah, actually, can you go back? So can you explain again what is GM?
GM of S, this is just this quantity. This is the expected value of the rank of the matroid, where the expectation is taken over all possible scenarios of the intersection of some set S and the set of types that have appeared in that scenario. So this is basically telling you the following. Suppose if I fix a set S of types, what is the maximum that you can allocate to this set? This is the rank of that set. And you can only allocate to a type if that type has shown up. So this should be the intersection of T and S, right? So in a sense, this is telling you how much you can allocate to this specific subset in expectation over all possible scenarios. So let me give you an example of a scenario, a problem that can be solved optimally by using this approach. Suppose you have you are in a display advertising. You want to sell contracts for display advertising. You have an advertiser. Each advertiser has a budget constraint, and each advertiser has a valuation for each type of impression, and they also have a cap on how many impressions of each type they want. And the advertisers are also partitioned into certain categories, and the search engine wants to ensure that from each category there is a cap of how many advertisers from that category get impressions of a certain type. And also suppose that your exact supply is not known because you're selling these contracts in advance. You don't know how many impressions you're going to get in the future. So this is something that can be modeled exactly in the framework that I explained, and we assume that all distributions are known. And you can solve this problem optimally. Like you can compute an auction for maximizing revenue optimally for this setting by using the framework that I explained in polynomial time. And like one thing that it's worth mentioning is that for each advertiser, I want to also specify a cap for the total number of impressions that the advertiser would get, then it would not, these constraints would not be a single polymatroid. It would be an intersection of two polymatroids. So that we still don't know how to handle. But for this, for a setting which is as like generalized what you have here, you can still solve it optimally in polynomial time. Okay, so the second part of my talk is decomposition via ex ante allocation rule. So I will try to go over this quickly, and this actually came before the first one. This is a paper from last year. Okay, so an ex ante allocation rule is defined as the following. Suppose for each agent, I will take the expected probability of allocation over all possible types of that agent. Like this is, for example, the sum of the products of these probabilities and this allocation, like 0.5 times 1 plus 0.5 times this. And you get a single number for each agent. And I call this the ex ante allocation rule. So it specifies that what is the expected probability that you allocate the item to the agent if you don't know the type of that agent. Now, I want to do some kind of decomposition similar to what I did with the interim allocation rules. And observe that the ex ante allocation rules are much smaller. Like, if you could use this, it would be another exponential reduction in the complexity of the problem, because the interim allocation rule specifies the probability for each type, whereas the ex ante allocation rule just specifies one number for the agent per each item or resource. So again, we face the following questions. How can we approximately decompose mechanisms via ex ante allocation rule? And when an ex ante allocation rule is feasible, and how can we compute the optimal or approximately optimal one? And how can we compute the optimal single agent mechanism subject to any ex ante allocation rule? So first of all, observe that if you have an interim allocation rule and we compute the optimal single agent mechanism, and if we then take the corresponding ex ante allocation rule and compute the optimal single agent mechanism corresponding to that, this is going to be larger in general than this one, because this faces less constraint. Because here you're specifying an upper bound on probability of each type. Here you're just specifying an upper bound on overall probability. So this suggests that by using the ex ante allocation rule, you will not be able to get the optimal, because this is like you would expect to get something which is like, I mean, this could be in general infeasible, the single agent problem that you get from solving this. Okay, But there's a condition that it has to satisfy for sure. So you can see that, for example, if you have 1 unit of item, the sum of the probabilities, ex-ante allocation probabilities, shouldn't add up to more than 1. This is always. But this is not, of course, a sufficient condition. Like, take this example. Suppose there are n agents. Each agent has a high type and a low type. The high type happens with probability 1 over n and requires an interim allocation probability of 1, and the low type doesn't get any allocation. And in this case, you can see that the ex-ante allocation rule for each agent is 1 over n, so it satisfies this semi-feasibility constraint. But of course, it's not feasible because what if 2 agents with high type appear at the same time? You cannot allocate to both of them with probability 1. But what you can do, what you can show is that you can actually get a 1 minus 1 over e approximation of any ex-ante allocation rule. Like, by scaling down these probabilities, you can actually implement this in a feasible way, and this is tight. So I will talk about this more in a minute. And I claim that there is some kind of multi-agent decomposition like before, which works as follows. Basically, in this decomposition, there are a bunch of single-agent mechanisms, and each single-agent mechanism allocates subject to some semi-feasible ex-ante allocation rule. And then there is a central allocation mechanism which tries to resolve the conflicts between the single agents because they could over-allocate. But it does it in a way that would ensure that every allocation is preserved with some probability gamma, which I will define later. So I will define this more precisely in the next slide. And I claim that gamma equal to 1 minus 1 over e can always be achieved. So this suggests that you can get a very good approximation, like you can get a 1 minus 1 over e approximation by using ex-ante allocation rule. So I will make it more formal in the next slide. But another interesting thing that I will show you, actually I will focus on the second one more, is that you can actually do it in an online fashion. And you get a 1/2 approximation.
So this archive is also achieved?
What's that?
The archive means achieved here.
Oh, it's, yeah, it means, so yeah, it means achieved, it's not archive. This is a typo. And so I will explain how this can be done by a reduction to the magician's problem, which is something that I defined. And then I will explain that in the next slide. But suppose that we could do that. Then I claim that an approximately optimal mechanism can be obtained by using ex-ante allocation rule as follows. Let's capital X denote the space of ex-ante allocation, semi-feasible ex-ante allocation rules. So if you have a single item for sale, this would be simply that inequality that the sum of the ex-ante allocation rules shouldn't be more than 1. Or if you have k units of item, shouldn't be more than k. Now, let's say this is the expected revenue of the optimal mechanism subject to some ex-ante allocation rule. Again, we show that this is always concave for any maximization problem in any setting. And you can get an upper bound on your optimal mechanism by solving this maximization problem. So this is not something that you can achieve. This is strictly an upper bound on what the optimal mechanism can do because these ex-ante allocation rules are semi-feasible. You may not be able to implement that feasibly. But I claim that you can always get at least a 1/2 factor of the upper bound in expectation by a reduction to the magician problem. Okay, so this is the interesting part, which is called the magician problem. So magician problem is the following. Suppose you have a magician and there is a sequence of boxes that arrive online and are presented to a magician. There is a prize hidden in one of the boxes, and the magician has k wands that he can use to open these boxes. If the magician uses a wand on box I, the box will open, but the wand may break with a probability xi, which is written on the box. And we know that the sum of these probabilities add up to no more than k, where k is the number of wands of the magician. Now, and we assume that everything has been arranged by an adversary, so the order of the boxes, the probabilities written on the boxes, and where the prize is hidden. And we want to obtain a good solution for this problem. And observe that in order for a magician to be able to guarantee that he gets the prize with a probability of, let's say, gamma, he has to ensure that every box in expectation is opened with a probability at least gamma. Otherwise, the adversary would just put the prize in the box that has the least ex-ante probability of being open. And I assume that the adversary, once he has arranged everything, he cannot make any changes. Like once the boxes have started arriving, the adversary cannot make any changes anymore. And furthermore, I assume that the magician has no prior information about anything, not even the number of boxes. The only thing that he knows is k. And I present a solution which is...
What does he sees? The boxes, each box that arrives?
Yeah, when you have the box... Yeah, when the box arrives, you see the number which is written on the box. You have to make a decision about the box, whether you want to open it or not. If you skip the box, you cannot go back to the box. You have to make it.
I guess your decision will depend on how many wands you have left. You have not broken so far.
Your decision depends on... Yeah, your decision is based on your past history and like the number that you... Actually, I show that the decision only depends on your past history. It's not even... It doesn't even depend on the number which is written on the current box. You can make a decision like only based on your past history.
But he do know that the summation of x bar is less than...
Yeah, that is what we know. But he doesn't know how many boxes are going to be there. Like, it could be, like, he doesn't know n. Like, whenever even when he sees the last box, he doesn't know if there's going to be another one or not. Okay, so I present an algorithm which I call the gamma conservative magician, which guarantees that each box is opened with an ex ante probability of at least gamma, and it tries to minimize the number of broken bands. And I prove the following theorem. I show that for gamma equal to this number or anything less than this, it never needs more than k1s. And observe that when k is equal to 1, this is 1/2. And when k gets larger, this actually goes towards 1. So which means that if you have large k, you can actually get something which is pretty close to 1. And here is how we can use it to like solve the... like this is just one example of how you can use the magician problem to solve the auction decomposition using ex ante allocation rule. Suppose you have k units of an item and you have unit demand buyers. You want to sell them to maximize in a way that would maximize your revenue. You solve this convex maximization problem, which is subject to these ex ante allocation rules being no more than k, and this gives you an upper bound on your revenue, clearly. But this is not, of course, obtainable. Now, what you do is you do the following. You create a gamma conservative magician with k1s, and you set gamma equal to this thing. And for each of the buyers, you do the following. You write this ex ante allocation rule on a box and present the box to the magician. If the magician opens the box, then you make the item available to the single agent problem corresponding to that mechanism, corresponding to that agent, which means that mechanism may either allocate the item or may not allocate, depending on what the type of the agent is. By this ex ante allocation rule, I know that the mechanism will allocate the item with probability at most this x hat sub I, right? And if it allocates, then I will go back and break the magician's wand. So you can see that the probability that the magician's wand gets broken is no more than this ex ante allocation rule, and they sum up to no more than k.
So if the prize is in that box, the magician still gets the prize even if the one breaks.
Yeah. The prize is actually irrelevant. It was just to make the justify why the magician wants to open every box with some probability gamma. I mean, the important thing is that the magician can guarantee that each box in expectation is opened with ex ante probability at least gamma. And because of this guarantee, you can actually get this fraction of every one of these single agent mechanisms in expectation. So overall, you get this fraction of revenue. And this can be extended to combinatorial auctions when you have multiple units, under certain assumptions. I don't want to get to the details of that. And the important thing about this is that this can be implemented actually as an online mechanism. Here, observe that the ordering in which the buyers are served is irrelevant, because I assume that you can serve them in any ordering. As long as you know what buyers are going to arrive in the future, you can solve this convex program, and then you can basically, whenever they arrive, you just do this thing. Like you write the ex ante allocation rule on a box and present it to the magician, and you decide whether to sell to the corresponding buyer or not. So here is a quick...
So one minute also. In your original problem, the online thing doesn't matter so much, right? But you're saying...
No, the original problem, there was nothing online. But I'm claiming that you can actually use it to do online. Actually, you can... I wish I had time to talk about this, but you can solve the online weighted matching problem, online stochastic weighted matching problem, weighted B matching problem, and with this technique and get this same approximation factor. Like you would replace K with B, where if you have like single one matching, you would get 1/2 approximation. That is tight, actually. So here is a sketch of how the magician works. So this is the easy part. The actual hard part is the analysis. So the magician actually computes a sequence of thresholds, theta 1 up to theta 1, and it computes these thresholds as he sees the boxes. And what the threshold, here is how the thresholds are used. Let's say Si is the random variable denoting the number of ones broken prior to seeing box I. If Si is less than the threshold, which means if we haven't broken too many ones, then I will open box I. If it is more than the threshold, then it does not open the box. And if it is equal to the threshold, it will randomize and with some probability open the box, where this exact probability comes from a dynamic program. And here is how the thresholds are computed. For each agent, for each box I will compute the theta I such that the probability of having broken less than or equal to theta I ones is at least gamma. And I will choose the minimum theta I that has this property. Like, this is something that you can compute by using a dynamic program, by having the knowledge of the probabilities written on the boxes 1 up to I minus 1, and by using the theta 1 up to theta I minus 1. You can compute these probabilities, and then you can choose theta I such that this is exactly this. And then once you have that, you basically, when you see the box I, based on the threshold and the number of ones that have been broken so far, you decide what to do with box I. And it's actually independent on the probability which is written on box I. That is the nice thing. So the dynamic program is easy to solve, and it's also easy to see why it works. The hard part is to show that when gamma is between 0 and this number, actually it could, when gamma is at most like this number, then this algorithm never uses more than k bonds, which means that these thresholds are never more than k. Because if a threshold is never more than k, it means that the magician never tries to open a box if he has already broken all of his k bonds. And also, I can show that no magician can guarantee a probability of more than this for opening every box. And so you can see that this is pretty close to that. So it's almost close to optimal. So to conclude, I presented a general framework for constructing Bayesian mechanisms in a variety of settings, as long as you can solve the single agent problem, which is exponentially simpler to solve compared to the multi-agent problem. You can get an optimal multi-agent problem. And the nice things about this approach is that you can have mixed classes of buyers in auctions. Like in most of the previous works, like you assume that like all buyers in the auction are similar. Like they all have budget constraint, or they all have additive valuations or things like that. But suppose you have an auction in which you have some agent has budget constraint, the other agent has risk parameter, and so on. And by using this reduction approach, you can actually mix all of them in one auction. As long as you can solve the single agent problem for each one individually, you can have all of them at the same time. It works for a variety of settings with non-quasi-linear utilities, arbitrary objectives, and even with online arrival. And notice that in all of the things that I explained, I never talked about the payments or the incentive constraints, because all of those go into the single agent problem. So as long as you can solve the single agent problem, you're fine. And some of these techniques, as I mentioned, for example, for the online stochastic weighted matching, you can apply this magician problem to obtain a very good bound. So that was the end of my talk. I would be happy to answer if you have any questions. Sure.
So one thing, you could clarify the relation between these two works you explained to us. So in the first, there wasn't any approximation ratio.
Yeah, the first one was optimal. The second one, you cannot get optimality, but to be honest, the second one is the practical one, because the first one, it relies on ellipsoid method, so it's purely theoretical. But the second one is actually pretty practical, because the magician problem just requires you to solve a dynamic program. And furthermore, the single agent parameters, you just specify the ex-ante allocation rule is just one number for each agent. It doesn't depend on the type space of the agent. Like the type space of an agent itself could be exponential, in which case you cannot use the first approach, but still you can get a very good approximation. And it tells you that actually one thing, one conceptual message of this is that when you extend this to combinatorial auctions, this condition of what the condition that you get is the following: if you have an environment in which the maximum demand of each agent compared to the total supply is less than 1 over k for some k, then you can get this approximation of the optimal. Which means if the demands of the agents are small compared to the total supply, you can get a very good approximation of the optimal without going through all the problems of like solving optimization problems over polymatroids. I mean, you just lose a very small, tiny fraction, but you get something which is practical. So
the other isn't this closely related to the contention resolution problem, which like this Wondrak and Chikui Wondrak study?
Contention resolution, I don't know about that.
Because, for example, right, so one thing you can do to really, it doesn't get you harm, but should get
Sorry,
you...
you mean for the first part or the second part?
Second, this problem itself. And like I said, that it wasn't online, but there's some like people I think have tried to study it on online setting. Because one trivial thing you can do is just say, I'm going to toss a coin for everybody independently with, let's say, xi by 2. If I see xi, I toss a coin with xi by 2.
Yeah, you get a 1/4 approximation, right? But here you get a 1/2.
Yes, 1/2, right? Yes.
Yeah.
So
So let me tell you one thing. What I explained was something which is very close to the optimum. But what you can do is that actually you can make a decision independently for each agent, and then like drop these boxes at random. And instead of this, you would get something which looks like 1 minus order of log k divided by a square root of k, or a square root of log k divided by a square root of k, something like that. But that is, I mean, that would be something which is good in asymptotically, but for a small k, it's not very optimal.
So like you toss a coin for everybody, and then the people who show up among them, you have to choose k of them, right? And
yeah,
you choose
something. Well, you can even do it online. Like you can, as they arrive, you toss a coin, and with some probability, you just keep them or you drop them.
Yes.
But if you do it that way, like this is an adaptive approach which decides based on the previous history. But if what you're saying is a non-adaptive approach, and you cannot get better than the, like I said, 1 minus a square root of log divided by a square root of k.
What are the open questions?
Okay, so good question. So some of the open questions are so first of all, what I explained, it settles the complexity of class of problems where you have polymatroidal constraint. But what if you have intersection of two polymatroids? So that is a pretty important class. Like if you have, for example, a bunch of items and you have a bunch of unit demand buyers, each one want at most one of those items, that's like intersection of two matroids. It's equivalent to intersection of two polymatroids. So how about those cases? Can we also compute the optimal mechanism for those in polynomial time? So that is one of the open questions. And yeah, I think that is the most, that is the important question I still have in mind.